Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll begin discussing angle measure. This video was produced for Ohio University Math 3110-5110 College Geometry. The corresponding reading for this video is section 4.5, The Measure of an Angle, from the book Geometry, a Metric Approach with Models by Millman and Parker. The corresponding homework is this short selection of only 4 exercises from section 5.1, but they are actually rather tedious exercises. The topics we'll be discussing are angle measure, protractor geometries, Euclidean angle measure, and finally the measure of a Poincaré angle. Our first topic, angle measure, begins with a definition. This symbol, script A, denotes the set of all angles in a Pasch geometry. And then we go right into the definition of angle measure. These words, angle measure or a protractor based on r subscript 0, are used when there is a Pasch geometry in the discussion and r subscript 0 is a fixed positive real number. Now what do those words mean? What they mean is a function denoted m, a function with domain, the set script A, that is, domain is the set of all angles, and whose range, that is, where the outputs come out, is the set of real numbers. And the function has these 3 properties, which are called the axioms of angle measure. Property 1 has to do with the range of values that can come out of this function. This symbol, m parentheses angle ABC, denotes the resulting output when an angle ABC is fed into this angle measurement function. So that blue number is the measure of an angle. And this first axiom says that the blue number, the measure of an angle, has to be greater than 0 and less than the number r subscript 0. Property number 2 is called the angle construction axiom. The angle construction axiom says this: given a half plane H, a ray BC on the edge of that half plane, and a number theta such that theta is greater than 0 and less than r subscript 0, given all that stuff, there exists a unique ray BA with A in that half plane H such that the measure of the resulting angle ABC is that number theta. Statement number 3 of the definition of angle measure is called the angle addition axiom. It says that angle measure is what's called additive in the following sense. If a point D is in the interior of an angle, then the measure of these 2 angles that are created add up to the measure of the angle that you started with, angle ABC. These 3 axioms of angle measure are a sort of wish list of properties that a function must have in order to be qualified to be called an angle measure. Now it's helpful to illustrate the statements of the definition of angle measure. So first I'll illustrate the angle construction axiom. So here's the statement that's the angle construction axiom. Now notice that it has some given stuff and then it has a claim. So I'll illustrate this with 2 drawings. The first drawing will illustrate all of the given stuff. So there's an illustration of the given stuff. We have the half plane H, we have this ray on the edge of the half plane, and I've just put down here this inequality showing that we have this number theta. Now I'm going to illustrate the claim. So there's our illustration. It shows that if you're given all this stuff, a half plane H, a ray BC on the edge of that half plane, and that number theta in that range, then there exists a ray BA that satisfies this property. That is, point A is in that half plane, and the measure of that resulting angle is that number theta. Now we'll illustrate the angle addition axiom. It's in the form of a conditional statement. If D is in that interior of that angle, then the measures of these angles add up. So I'll do what I often do when I illustrate a conditional statement. I'll draw an illustration that shows the hypothesis, and then another illustration that shows the conclusion. There's the illustration. On the left is a drawing that shows the hypothesis. We have a point D in the interior of an angle. On the right, we have a drawing that shows the conclusion. The measures of these two small angles add up to the measure of this large angle. Let's go on. Now, what's up with this symbol r subscript 0? In the definition of angle measure, this r subscript 0 shows up there in the name of the angle measure, and then it shows up here in axiom 1, and it shows up here in axiom 2. What is it? Well, most commonly we use r subscript 0 equals 180. In that case, the measure of an angle is greater than 0 and less than 180. Notice, no straight angles. When r subscript 0 is 180, the angle measures are sometimes labeled as degrees. So, for instance, if the resulting measure of an angle was 2, we'd say that the measure was 2 degrees, or we would denote it this way, 2 with the superscript little open circle, a little degree symbol. It's also common to use r subscript 0 equals pi. In that case, the measure of an angle is always a number greater than 0 and less than pi. When r subscript 0 is pi, the angle measures are sometimes labeled as radians. So if the angle measure was the number 2, we would say that the measure was 2 radians. A more obscure choice is to use r subscript 0 equals 200. In that case, the resulting angle measure for any angle is greater than 0 and less than 200. When you use that r subscript 0 equals 200, the angle measures are sometimes labeled as gradients. So if the angle measure were 2, we would say that the angle measure is 2 gradients. I'll remark here that calculators offer degrees, radians, and gradients with a DRG key. In our book, from now on, we'll use only r subscript 0 equals 180. Since that's the only value of r0 that we'll ever use, we won't bother saying degrees. We'll just say, for instance, the measure of angle ABC equals 2. And we won't say this. We won't say the measure is 2 degrees. So we've talked about angle measure. Now I want to talk about what are called protractor geometries. A protractor geometry is an ordered quadruple, script P, script L, D, M, such that the ordered triple, script P, script L, script D, is a Pasch geometry, and M is an angle measure that works for that Pasch geometry. So again, the protractor geometry is all 4 of those things. In today's video, we'll be discussing 2 examples of protractor geometries, the Euclidean plane and the Poincaré plane. Now I'm going to discuss Euclidean angle measure. Those words, Euclidean angle measure, mean this: a function denoted m subscript e with domain the set script A, where script A is the set of angles in R2, and range the set of real numbers. That function m subscript e is defined by the following formula. The measure of an angle ABC is obtained by using this formula, cos inverse of that mess. Now, I should explain a bit about this formula. First of all, we use degrees for the cos inverse function because we're always using r0 equals 180 in our course. Also, this expression, a minus b, is the Euclidean vector from b to a. Now, it's a fact from proposition 5.1.2 in the book that this function does have properties 1, 2, and 3 set forth in that definition of angle measure that I discussed a while ago. So this function is qualified to be called an angle measure for the Euclidean plane, the Euclidean plane Pasch geometry. So in other words, this collection of 4 items is a protractor geometry. It's also called the Euclidean plane. Now, it's an interesting fact that we won't discuss, but it is discussed in the book in exercise 5.1, number 5, that this same function, m subscript e, is qualified to be called an angle measure for the taxicab plane Pasch geometry, R2 with Cartesian lines and the taxicab distance function. So in other words, this ordered quadruple, R2 with Cartesian lines, the taxicab distance function, and the Euclidean angle measure, is a protractor geometry. It's also called the taxicab plane. I want to remark briefly on the connection to the dot product. In previous courses, you might have seen expressions like this, that v dot w equals the norm of v times the norm of w times the cosine of the angle between them. Well, if we take that equation and divide by that product of those two norms, we get this new equation. Now here we have to assume that both vectors are non-zero, because you can't divide by 0. But that's okay, because we'll be using this in calculations where we're talking about angles, and those vectors will be non-zero. Now if we use the angle bracket notation instead of the dot product, we get this new equation. That thing in the numerator we now call the inner product of v and w, or bracket v comma w. And then finally, if we take a cos inverse of both sides, we get this new equation. So we see that this thing on the left is a calculation that results in an angle, or an angle measure. So for an example, let's let a equals 0, 1, b equals 0, 5, and c equal 3, 4. Question A is to compute the Euclidean angle measure of angle ABC. And the instructions are to give an exact, simplified answer and a decimal approximation rounded to 2 decimal places, and to show all steps clearly. Well, let's go back and look at our formula. We need to compute this. So we're going to need to build all these expressions and then find the value for this. So this is a rather tedious example, and now I do a bunch of these examples in this video. We're not going to walk through them step by step. You can read the notes to do that, but I want to point out that the way to do these calculations is to take them seriously and to keep very careful notes. Notice that I write things like this. I write down what I'm going to do before I do it. I have explanations of every calculation that I'm doing. I don't just have floating calculations without some kind of explanation of what they are. And in the end, you'll see that I do this calculation. So when you do your work, you should do the same kind of thing. You should have a bunch of calculations, but you should have a bunch of headings explaining what these calculations are that you're doing. So our goal is to build all the stuff we need to do this. So here we go. First thing I do is I build this expression, a minus b. Remember, that's called the Euclidean vector from b to a. Now that calculation is simple. I just do a vector subtraction and I get this value for that quantity. Then I'm going to need this expression. That's called the norm of that vector. So I put that title there saying that's what I'm going to do, and then I do it. Now remember how that norm is computed. The norm of this vector is the x-coordinate squared plus the y-coordinate squared. The result is that norm is the number 4. And then it goes on in a similar fashion. I compute this quantity, which is called the Euclidean vector from b to c. I get that vector. I compute the norm of that vector, and I get that number. And then finally, I compute the inner product of those two vectors. That expression is an expression that I need in order to do this calculation, and I give it a name. It's the inner product of those two Euclidean vectors. Remember how to compute the inner product of two vectors. You take the product of the x coordinates, and you take the product of the y coordinates, and then you add them together to get this result. Now looking ahead, I need to build this. That is, I need to take that inner product that I just computed, and I need to divide it by the product of those norms. So I write that title. I'm going to divide that inner product by the product of the two norms. That calculation looks like this using those results from before, and I just get 1 over square root of 10. Now finally, we're able to compute the Euclidean angle measure. We have that expression, which is going to go inside of that cos-inverse function, and my result is this. That's my answer. Remember, the instructions were to give an exact answer. That's it. Notice that I have not used a calculator in my computations, or there are no decimal approximations anywhere in what I've done so far. That thing that I've got circled is the only way to write that number exactly. Now finally, here at the very end, I can type this into a calculator or into Wolfram Alpha, and I get this decimal approximation. So again, your instructions are to give an exact simplified answer and a decimal approximation. Notice that my answer is simplified. For instance, here, I simplified that expression to 1 over square root of 10. This expression is simplified. So the result of question A is there's this exact answer and there's this decimal approximation. All right, question B is to compute the Euclidean angle measure of angle BCA. Well, we do the exact same sort of thing. Our goal is to build that expression and find its value. So you can see that I do the same kind of steps that I did in part A. I find this Euclidean vector, and then I find its norm. I find this Euclidean vector, and I find its norm, and so forth. In the end, I end up with this exact simplified answer, cos inverse of 1 over square root of 5. And then at the end, I typed that into a calculator. Actually, I used Wolfram Alpha, and I got this as the decimal approximation. And then finally, question C, compute the Euclidean angle measure of angle CAB. Well, it's the exact same thing that we just did in the previous two examples. I find this vector, and then I compute its norm. There's its norm. I compute this vector, and then I find its norm. I compute this inner product of those two vectors, and I get that number. And then I divide that inner product by the product of the two norms to get this result. And then finally, I'm able to use that as the argument, as the input to the cos inverse function, and I end up with this answer, cos inverse of that. So there's the answer. Now, when I type that into Wolfram Alpha, I get actually 45. That's exact. So I don't need to keep this messy expression. 45 is the exact answer. Question D is to compute the approximate angle sum of that triangle, just approximately, and to give a decimal approximation rounded to 2 places. Well, using the results from before, the measure of angle ABC plus the measure of angle BCA plus the measure of angle CAB, just the approximate results, I get these numbers, and they add up to 180.00. Question E is to illustrate the results from the previous parts. Well, I've got this drawing that I made in Desmos. Now I'll label it. Desmos doesn't have a very nice way for me to label letters. So 0, 1 is point A, 0, 5 is point B, 3, 4 is point C, and then measure of angle ABC, this number, 71.57, goes here. The measure of angle BCA, that number, goes here. And finally, the measure of angle CAB, that number, goes here. That's the end of that example. Let's go on. Now I want to talk about the measure of a Poincaré angle. So we have a way of measuring angles in the Euclidean plane. What do we do in the Poincaré plane? Well, the method is to find the Euclidean tangent vector to the circular arcs at the point where they intersect, and then measure the angle between those tangent vectors just using regular Euclidean angle measure. So I'll illustrate that on this drawing here. Here I've got two lines in the Poincaré plane. These circular arcs are lines. Now I can imagine a tangent vector here. That's a Euclidean tangent vector drawn to that circular shape, and another tangent vector here. So now I've got these two straight-looking vectors, the red one and the green one, and I can just simply find the measure of the angle formed by those vectors using Euclidean angle measure. Now, we know how to find angles using Euclidean angle measure. The question here is, how do we find these vectors that we'll use when we do that? Find the angle between those vectors, the green vector and the red vector. Well, the book presents this definition of the Euclidean tangent to a Poincaré ray. So if point P is this point in the upper half plane and point Q is this point in the upper half plane, then the Euclidean tangent to Poincaré ray PQ is defined to be the vector denoted capital T subscript PQ. Now, it's given by different formulas in different cases. If line PQ is a type 1 line, then this expression represents this vector computed using this formula. If line PQ is a type 2 line and x subscript p is less than x subscript q, then this symbol denotes this vector. And finally, if line PQ is a type 2 line and xp is greater than xq, then this symbol denotes this expression. Now, the book's presentation of this definition is very concise. It's a standard style of presenting a function that's got different formulas in different cases. But it will be helpful to have a clear procedure for computing TPQ in practice. Notice the first thing you have to decide is what kind of line you're dealing with. And the way that you do that is by scrutinizing the relationship between the x-coordinates of point P and point Q. So I have put together a procedure where you start by scrutinizing those x-coordinates and then go from there. So here's my procedure for computing that Euclidean tangent to a Poincaré ray, PQ. If the 2 points have the same x-coordinate, then that line is a type 1 line, and that vector is given by this formula. If xp is less than xq, then line PQ is a type 2 line, and you need to find the C and the R in order to build this. Well, you need the C, but I'll discuss this more later. So you have to find the value of C and then build this expression for that tangent vector. On the other hand, if xp is greater than xq, then again, line PQ is a type 2 line. Find the values of C and R and build this expression, build that vector. Now, notice that in the case that line PQ is a type 2 line, that is denoted by this symbol, CLR, the computation of that vector, TPQ, only needs the value of C for the line. Notice these formulas only involve the letter C, not the letter R. So that red number C is used, the green number R is not used. So the value of R is not used, but I feel it's important to find both C and R for two reasons. For one thing, when making an illustration of ray PQ, it's important to label the line CLR. Also, to double check my results, I plot P, Q, and line CLR in Desmos. So I need to have the value not only of c, but also the value of r in order to type the expression that describes that line into Desmos. Now recall from earlier in the semester, from section 2.1, the procedure for finding Poincaré lines. So given a point P with those coordinates and point Q with those coordinates that are any two distinct points of the Poincaré plane, here's the procedure for finding the Poincaré line. First of all, if the 2 points have the same x-coordinate, then the line that they both lie on is a type 1 line with that description where a is that number that's the common x-coordinate. On the other hand, if the 2 points have different x-coordinates, then we find the constant c by doing this calculation, and we find the constant r by doing this calculation. And then we build this symbol CLR using those two numbers, c and r. So that's all kind of a blast from the past. So let's go back up and remember what we're doing. So our goal here is to find the measure of a Poincaré angle. So I have in this picture a Poincaré angle made up of a green ray and a red ray. And remember, our strategy is going to be find that Euclidean vector and find that Euclidean vector, and then find the Euclidean measure of that angle formed by those two vectors. So far I've discussed how we're going to get these vectors, this red vector and this green vector. Now we're ready to discuss the official definition of the measure of a Poincaré angle. So these words, Poincaré angle measure, mean this function, this should say m subscript h, with domain script a, where in this case script a denotes the set of all angles in the upper half plane, and the range of the function is the set of real numbers. And the function is defined this way. The measure of an angle, the Poincaré measure, is obtained by this formula. So notice that that expression on the right is the Euclidean angle measure of the Euclidean angle formed by those vectors TBA and TBC. That's that pair of red and green vectors from that diagram up above. And so if we've got those two vectors, we find their inner product, we divide the inner product by the norms, by the product of those two norms, and then we find cos inverse of that. Another remark, we used degrees again for cos inverse because, again, we're using R0 equals 180 in our course. And again, remember that this expression TBA is the Euclidean tangent to Poincaré ray BA at point B. Now, it's a fact in the book presented as proposition 5.1.4 that this function does have properties 1, 2, and 3 set forth in the definition of angle measure. So in other words, it's qualified to be called an angle measure for the Poincaré plane past geometry. So in other words, this ordered quadruple, the upper half plane, the Poincaré lines, the Poincaré distance function, and this Poincaré angle measure, that collection of four things is qualified to be called a protractor geometry. Now it's also called the Poincaré plane. So for example, let's let A, B, and C be the same three ordered pairs that we had in example 1. We're going to do the same things that we did in example 1. We're going to compute the measure of the three angles, but in this example, they're going to be Poincaré angles. And we're going to give exact simplified answers and decimal approximations for each. So in part A, our goal is to compute the measure of Poincaré angle, ABC. So we need to do one of these. So our strategy will be to get these parts that are used in this expression, build this expression, and then find its value. Now notice my approach is the same that I used in the previous example. I have titles for every calculation that I'm going to do. So I have a bunch of calculations, but for each of these calculations, I have a sentence saying what it is that I'm going to be doing. All All right, our first job is to find Poincaré line BA. So we scrutinize these 2 points. Since they have the same x-coordinate, line BA will be a type 1 line, denoted as 0L. Now we have to compute the Euclidean tangent vector to Poincaré ray BA, and I should say at point B. Now remember how we do this. I have a procedure a few pages back. This procedure for computing the Euclidean tangent vector, I scrutinize the x-coordinates of the points, and then based on what I find, I do one of these 3 things. Well, in the case of ray BA, I can compare the coordinates for points A and B. Since those have the same x-coordinate, the Euclidean tangent vector will be given by this formula. So I build that expression, and I get that ordered pair. That is a tangent vector. Now I compute the norm of that tangent vector. So the norm of that vector is obtained by finding the square of the x-coordinate and the square of the y-coordinate and adding them together and then taking the square root, and I get the result of 4. So there I've done a bunch of stuff that was all about getting that part and that part that I'm going to use when I build this expression. So there's that part and that part that I need. I'm also going to need this part and this part. So that's what's next. Now in preparation for finding those next parts, I'm going to need to find Poincaré line BC. So for that I'll scrutinize these points. Notice that they have different x-coordinates. So Poincaré line BC will be a type 2 line. So I need to find the value of C for that line. I am also going to find the value of R, even though I don't need it right away. Well, to find the value of C, I set up that calculation, and I get the result that C is the number 0. To find the value of R, I set up that calculation, and I get the value R equals 5. So Poincaré line BC is the type 2 line 0L5. Now I need to compute the Euclidean vector tangent to Poincaré ray BC at point B. Well, again, I follow my procedure from a few pages back. I scrutinize the x-coordinates, and depending on what I find, I do either this or this or this. Well, in this case, since xb is less than xc, the Euclidean tangent will be obtained by using this formula that I pulled from that procedure. So when I build this expression, I use that value of c that was the number 0 that I got a while ago, and I end up with the result, this ordered pair 5, 0. That's the Euclidean tangent vector denoted by the symbol t subscript bc. Now remember, I'm also going to need the norm of that vector. So I'll do that now. Compute the norm of that Euclidean tangent vector. So the norm of this vector is denoted that way, and it's computed by doing this calculation. You square the x-coordinate, you square the y-coordinate, you add them together and take the square root, and the result is that norm is the number 5. Now I need to build this expression. I need to find the inner product of those two Euclidean tangent vectors. Well, to find this inner product, I have to go get this vector from the previous page. TBA is that vector, 0, -4. So that vector goes here. TBC, I just found it's 5, 0, so that vector goes there. Now when I compute the inner product, remember what I do, I multiply the x-coordinates together, and I multiply the y-coordinates together, and I add those two results, and I get the number 0. Then I divide by the inner product of the two norms to build this expression. That expression is just going to be the number 0. So now I'm ready to compute the measure of Poincaré angle ABC. So I take that number 0 and I put it in there, and I get this, cos inverse of 0. And I get the number 90. Remember, cosine of 90 degrees is 0. So cos inverse of 0 is 90 degrees, or as we'll say in our course, just plain old 90. And notice that's an exact answer. Let's go on. Question B is to find the measure of Poincaré angle BCA, give an exact simplified answer and a decimal approximation, show all steps clearly. Well, let's look forward. Our goal is to do this calculation. We're going to need all these parts. So I follow a procedure just like I did in part A. I write down the calculations that I'm going to do before I do them. So I'm going to, in the first few lines, find this Euclidean tangent vector and its norm. Remember though, in order to do that, I have to figure out, first of all, what's up with Poincaré line CB. Well, it gets easier as you go along because we already found in part A that Poincaré line BC is this type 2 line. Now we go on to find the Euclidean vector tangent to the Poincaré ray CB at point C. Well, we follow my procedure from a few pages back. I scrutinize the x-coordinates, and then depending on what I find, I either do this or this or this. Well, when I scrutinize the x-coordinates, I find that xc is greater than xb, so this is the formula that I use to build the Euclidean vector tangent to that ray. Now when I build this expression, I use the value of c for my line, and I get the result that the tangent vector is minus 4, 3. When I compute its norm, I get the number 5. What's next? Well, I need to find this vector and the norm of that vector. Tangent vector to Poincaré ray CA. Well, in order to do that, I'm going to have to first investigate Poincaré line CA. Well, since points C and A have different x-coordinates, Poincaré line, this should say CA, will be a type 2 line. So I have to find the value of its center, C. When I use that formula to find C, I find that the center is at 4, 0. So the value of C is the number 4. I don't need it right now, but I'm going to go ahead and get it. The value of R is square root of 17. So Poincaré line CA is this type 2 line, 4L square root of 17. Now we're going to compute the Euclidean tangent vector to Poincaré ray CA. Remember that I used that procedure that I set forth a few pages ago. I scrutinized the x-coordinates. Since xc is greater than xa, I use this formula for finding the tangent vector to Poincaré ray CA. The thing to notice though is that I am using the value of c that goes with line CA. That value of c is 4. The previous calculation used a value of c that was the number 0 because line CB had a value of c that was 0. So when I build this expression and find its value, I get the ordered pair -4, -1. Then I'm going to need the norm of that vector there and there. So I compute the norm the standard way and I get the value square root of 17. Now in order to build this, I'm going to need the inner product of those two vectors. So I do that next. And again, I always say what I'm going to be doing. I get the result that the inner product is 13. Finally, I'm able to build this expression, and I get 13 over 5 square root of 17. Notice that I don't get a decimal for that. I just leave that expression in exact form, so that I can then compute the measure of Poincaré angle BCA. It's this expression. That's the only way to write that expression exactly. So again, if you type this into a calculator, then you're not going to have an exact expression. You're only going to have an approximate expression. So the only way to write this angle measure exactly is to leave those symbols as they are and write that. And then I can type all of this into Wolfram Alpha or into a handheld calculator, but I like Wolfram Alpha better, and I get this decimal approximation. Let's go on. Question C is to compute the measure of Poincaré angle CAB. Well, I won't go through these steps. You can go through them in detail, but it's the same thing that we did in parts A and B, and nothing surprising happens. The result is the measure of Poincaré angle CAB is this expression written exactly. That's approximately 14.04. So again, when you do these calculations, don't type them into a calculator. Leave them as exact expressions, because you're going to need to have an exact expression at the end. Now finally, question D, compute the approximate angle sum of the Poincaré triangle and give a decimal approximation. Well, the angle sum for that triangle is those three angle measures that we found in the last parts A, B, C. So part A, we found that angle measure was 90. In part B, we found that angle measure was 50.91. In part C, we found that angle measure was 14.04. The resulting sum is 154.95. Question E is to illustrate the results from the previous parts. Well, here are those same 3 points, but this time those are points of a Poincaré triangle. So the sides of the triangle are segments, Poincaré segments that are part of Poincaré lines. So I need to label those lines. Now I can put in the angle measures. So there's our illustration. Notice again, I needed the values of R in order to be able to correctly label those lines. And also I use them to type the formulas for these lines into Desmos and get this nice graph. It's interesting to compare the results of examples 1 and 2, since they use the same 3 points, A, B, and C. So in example 1, the 3 angle measures were here, and they added up to 180. In example 2, the Poincaré case, the angle measures were here, they added up to 154.95. So notice a couple of things. Sometimes the Euclidean angle has a larger measure than the Poincaré angle. In those two cases, the Euclidean angle had a larger measure. But sometimes the Poincaré angle has the larger measure, such as in that case. Angle ABC was larger in the Poincaré plane than in the Euclidean plane. The other thing to notice is the angle sums. It's no surprise that the Euclidean triangle had an angle sum of 180. You've been familiar with that for years. But what's surprising is the Poincaré triangle has an angle sum that's less than 180. Well, that's the end of the video. Thank you.